Today we're going to talk about the unit circle. It's our intro to the unit circle. It's one of our bigger days of the year, probably the biggest day in terms of getting ready for pre-calc. I'm going to teach a few ideas, three of them that will sort of hang out there unattached for a while. And then after we've kind of seen them and established what these ideas are, we'll bring them all together and I'll make one big megazord, which none of you probably know of because you had horrible childhoods, but megazords are from Power Rangers. The first idea is about reference angles and degree, or radians and degrees, but really reference angles. If I draw some angle, like so, that can be measured in radians or degrees, either of those measure angles. And I can always draw a line straight down to the x-axis that gives me some sort of a right angle and some sort of a degree theta from the x-axis. And as that ray moves around, the angle theta that came with it is also going to move around. So now I can draw this segment down here to the x-axis, and this is now a right angle, and this is now my theta. So with these radians and degrees, the theta that we're talking about, the angle, is always the angle down towards the x-axis. It's always going to be the piece that's the x-axis. It's not always going to be the smallest piece. Like if I come here, well, the angle theta is now this part right here, which is actually the bigger chunk, and that's my angle theta. But the idea of a reference angle, which is the new thing we're introducing here, is that I can take any angle that we have in any quadrant, and when I think about the triangle that it makes with the x-axis, I can construct a similar, in fact, a congruent triangle in the first quadrant. And that congruent triangle is going to have the same angle theta right here. This is called the reference angle. It's when you take an angle that's in a different quadrant, something in quadrant 2 or 3 or 4, you take an angle that's not in quadrant 1 and you put it in quadrant 1. There's my quadrant 1. Any angle or any degree that's in any place where you don't want it, it can be moved to the first quadrant using a reference angle. So, for example, I could have this angle way over here. Well, then my theta right now is here. So I'm coming off of this triangle. The reference angle would be the same theta over here, but now it's in quadrant 1. Since we'll say, suppose this right here is something like, I don't know, 25 degrees, then this theta here would also be 25 degrees. It's always going to be the same angle measure. That's why we can use the same theta. And if I took that piece and I put it way out over here, the reference angle would also be way out over here. And so if this is, let's say, 31 degrees, this is also 31 degrees. That's a reference angle. Taking something that's in quadrants 2 or 3 or 4 and putting it in quadrant 1. Because then things are positive and nice and easier to calculate. I can show it with Sketchpad. This terminal angle is the initial original angle. And notice how it's always forming something going to the x-axis. Well, if this is my terminal angle, then this over here is my reference angle. Where'd you go? You're there. That's where the angles between the x-axis are the same. This angle in here is the same as this angle in here. I can move it around. If it's way up here, the reference angle is way up here, because now this angle is the same as this angle. Sorry, things moving around so weird. And if I put it way over here, the reference angle is way over here. Reference angles are always in quadrant 1. If from the center, from the origin, I travel 5 units right and 3 units up, where do I end up? Where is the terminal point? Well, obviously, if I go 5 units right and then 3 units up, that is the point 5, 3. Not a lot of rocket science there. But the idea that I'm trying to stress is that a coordinate is really just a distance. I end at the point 5, 3 because a coordinate really just measures distances. An x-coordinate is a distance from the y-axis. So this 5 here tells me that I'm 5 units from the y-axis. And this 3 here tells me I'm 3 units from the x-axis. I'm just measuring distances. Coordinates are distances. They can have positive and negative because that implies direction. But that's not a concern right now. I'm going to keep that same idea of coordinates as distances, but now I'm going to find this coordinate right here as a point, xy. How can I do that? Well, we're doing trig, so I'm going to draw a triangle. And the triangle is going to go to the x-axis. It's always going to the x-axis. So this angle here, this is my new theta. My theta is now 50 degrees. I want to find this side length x and this side length y. Well, to find x, I know that the cosine of 50 degrees is x over 3. Adjacent over hypotenuse. I picked cosine because that's going to give me the adjacent side compared to that 50. That means that 3 times the cosine of 50 is x. If I do 3 cosine 50, make sure you're in degrees. I am. 3 times the cosine of 50 is 1.9. So my x value here is about 1.9. Well, to find y, this is the opposite side of this new triangle, this right triangle here that I'm looking at. So to find y, I do the sine of 50 is y over 3. So 3 sine 50 equals y, and 3 times the sine of 50, that one. 3 times the sine of 50, 2.3. So this xy coordinate I have up here is really the point 1.9, 2.3. Because this distance is the same as the x coordinate, and this distance is the same as the y coordinate, because coordinates are just distances. The third idea is one that we've seen before. Oops. I'll come back to that. The sines and cosines that we use. Give me just 1 second. Hi, Emily.
Are you recording?
I am. It's okay. On our last slide, we took a radius of 3 units. We can take that same radius of 3 units and make it a radius of 1 unit. If we make it a one unit radius, 1 unit hypotenuse, or I should use the term hypotenuse, all of these lengths here have a length of 1, have a radius of 1, or they form a triangle that has a hypotenuse of 1. So if we think about all of those possible triangles we could draw from the center, it starts to form a circle. Since the radius is 1, we call it the unit circle. Okay, we'll come back to this idea a little bit later, but this circle is made up of all the possible triangles that have a radius of 1. In fact, let's not come back to it. Let's do something now. I'm going to give a new this right here. Let's say that this angle is, I don't know, 18 degrees. Well, this hypotenuse is 1. To find the value of this coordinate, xy, I would think about this right triangle. Well, this is the height y, and this is the distance, horizontal distance x. I know that the cosine of 18 equals x, and the sine of 18 equals y. It's really x over 1 and y over 1, because that's opposite over hypotenuse. But the hypotenuse is just 1. So really, x equals cosine 18, y equals sine 18. And I can make that cosine and sine Hey, we're interrupted, sorry. Here's what I'm trying to get us to. I could draw any angle. I'll change the color so it's a new one. I'll go purple. Purple's fun. Well, this angle theta that comes from inside here, this angle theta is how I can find x and y. X is cosine of theta. Y is sine of theta, because that's how you can find those x and y coordinates. based on these triangles that we can draw. And now this idea, the way that I drew it here, is a little bit off, but we'll live with it for now and keep going. Our third idea is special right triangles. We've talked about these a lot. If this hypotenuse is 1 and this is a 45, 45, 90, then that's a root 2 over 2, and that's a root 2 over 2. If this is 1, this is a 30, 60, 90, and this is a 1/2, and this is a root 3 over 2. What I can do is I can take these triangles, that's all connected. I can take these triangles and put them on my unit circle. I come over here, the circle that we just drew, and I paste that triangle that I just copied. Well, because this length here was root 2, this coordinate up here, I'm sorry, is root 2 over 2. And since this length here was root 2 over 2, the y coordinate is root 2 over 2, and we can find that point on the circle. We can do it again with another one. We can change all this to blue. Move it over here first. So here's root 3 over 2, and here's 1/2. Let's make blue. And let's make you blue. Why not? We'll make you blue. Could be fun. Group all this up. Can I grab you? That's fine. Group all this up. We'll copy it. And we'll paste it. Have a new triangle with a new coordinate, and this coordinate is at root 3 over 2, comma 1/2. This point right here is root 3 over 2, comma 1/2. I can do the same thing one more time, and instead of using a 30-60, I can use a 60-30. So I'm going to ungroup all this. I'm going to ungroup all this. Let's pull this triangle out over here. Twist it. Flip it. So this hypotenuse is still of length 1. This length is now 1/2. And this length is now the root 3 over 2. And when I show this third triangle, it gives me a third. Let's set the point. Root 3 over 2, comma 1/2. Well, since I found those 3 points, there's no reason I couldn't find more points also. There's no reason I couldn't grab this triangle, and this triangle, and this triangle, and ungroup everything. Clear all my writing. I'm going to group these 3 up together. Clone it. So one of these we've already had. But now we can take another one and find 3 more points. Then we can take another one and find 3 more points. And then finally we can take one more flip it around and find these last 3 points. So now I have this point here, which is root 3 over 2, 1/2. This point here, which is root 2 over 2, 1/2. And this point here, 1/2 comma root 3 over 2. And all those points are going to get reflected here and 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 here, and just their signs will change. Some positive, some negative. So we can have negative 1/2 comma root 3 over 2, negative root 2 over 2 comma root 2 over 2, negative root 3 over 2 comma 1/2. Hopefully you get the idea. When I fill all that in, there's something that's going to look more like this. This is a cleaner version of this. This is the unit circle. You're going to live and you're going to die by it. You're going to get it all filled in. It's going to be a beautiful thing. We'll be back in a second to talk about that. So we can fill in this unit circle with all of those ratios that we've been seeing this whole way through. It's actually going to start down with triangles. The special right triangles are the key. If this is 45 degrees, and this is 1, then this is root 2 over 2, and root 2 over 2. If this is 30 degrees with a hypotenuse of 1, then this is 1/2, and this is root 3 over 2. Now think about this 30, 60, 90 right triangle here. That's the same as this 30, 60, 90 right triangle here, even though we don't really draw this vertical segment very often. But if this is 30 degrees, whoops, sorry, that was 0 degrees. If this is 30 degrees, and this length here is root 3 over 2, coming from this length here. And this is 1/2, also coming from that length down here. And we've done a 45 degree right triangle. It has root 2 over 2, comma root 2 over 2, coming from these values down here with this triangle. And this 60 degree triangle has a 1/2 for the x and a root 3 over 2 for the y. Since all these radii are 1s, the radius of this circle is 1, this point out here is the point 1, 0, and that's at 0 degrees, which is the same as 360 degrees. So I can take all these points that we just copied down and think about how they reflect. First of all, this is the point 1, 0, this is the point 0, 1. But this point here is going to be a reflection of this point here. So it's negative 1/2 root 3 over 2, negative root 2 over 2, root 2 over 2, root 3 over 2, 1/2. Keep on going. These points are reflections of these points. This is a negative right there, if you can see it. So now I have negative root 3 over 2, negative 1/2, negative root 2 over 2, negative root 2 over 2, and then negative 1/2, negative root 3 over 2. This is the point 0, negative 1. These points here and these points here are reflections of each other, so 1/2, negative root 3 over 2, root 2 over 2, negative root 2 over 2, root 3 over 2, negative 1/2. We filled in all the points. Doing the angles is also pretty easy. I mean, if this is 30, and that's 60, then that's 90. And then there's 120, and 150, and 180, and 210, and 240, and 270, and 300, and 330, and 360, which we've already got. Unless I skipped all these middle 45 ones, I skipped this one, and this one, and this one, because 45 isn't a multiple of 30. So I'm going to count by the 45 as well. Here's a 45, there's a 90, there's a 135, there's a 180, so 225, 270, 315. I just counted by 45s, and now all the degrees are done. What's left is the radians. Radians I'll go a little bit slower on, because I think they're the most confusing. We know that 0 degrees and 0 radians are the same, and hopefully you remember that 360 degrees is 2 pi radians, or that a whole revolution is 2 pi radians. So if a whole revolution is 2 pi radians, then half of a revolution here would be pi radians. Oops, I missed this point. Half a revolution is pi radians. So half of that would be pi over 2 radians. So 90 degrees equals pi over 2 radians. You don't need to write that down because that's what this is saying right here. 90 degrees is pi over 2 radians. The one that you've used before is that 100 degrees is the same as pi radians. Well, let's think about this one first. 90 degrees is pi over 2. 45 is half of 90, so this will be half of pi over 2 or pi over 4. 45 degrees is pi over 4 radians. And now I'm going to think about counting by 45 degrees, just like how we've already done. We went 45, 90, 135, 180. I'm going to do the same thing, but instead of counting by 45s, I'm going to count by pi over 4s. This was a pi over 4. So this is 2 pi over 4, and 2 pi over 4 reduces to pi over 2. So this is 3 pi over 2. This is 4 pi over 2, or just pi. This is 5 pi over 2. This is 6 pi over 2, or 3, over 4, excuse me. I'm doing all that backwards. I'm going to start over. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. This one here should be 5 pi over 4. Which makes this one 6 pi over 4, which will be 3 pi over 2. And then 7 pi over 4, and then 8 pi over 4 is 2 pi. For 90 degrees, something goes in red just to keep them separate, or I'm sorry, for 30-degree chunks. 30 degrees is 1/3 of 90. Which means that if we have pi over 2 radians, which is what this is here at 45 or 90 degrees, we do pi over 2 times 1/3, we get pi over 6. So 30 degrees is pi over 6 radians. So this is 1 pi over 6. I'm just going to count by pi over 6s. There's a 1 pi over 6, there's 2 pi over 6, and 2 pi over 6 is really just pi over 3. Here's 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, which is really 5 pi over 3, and 11 pi over 6. Followed up by 12 pi over 6, which is 2 pi, and you finished off your unit circle. The important thing about the unit circle is to remember that cosine is x and sine is y. So now if I asked you, like, what's the cosine of 150? You'd go to 150 degrees and look at the x value, and that's -√3 over 2. You can check that in your calculator if you want. And if I asked you, what is the sine of pi over 4 radians? Well, pi over 4 radians is right here, so the sine of that is going to be the y value, or √2 over 2. That's probably enough for today. Hope that was helpful. Enjoy the rest of your evening.